Our next topic, inverse functions. We did touch on this a little bit last year, you might remember, when we were looking at functions. Now we're going to look at the topic in a little bit more depth. But a reminder of what we saw last year. What it basically is, right? We know the definition of a function, and that being for every x in the domain there's a maximum of one y value. Visually it would satisfy the vertical line test. Okay? The relation that we obtain by swapping the x and y's around. So all we do is swap the x and y's around in the equation of the function. That's known as the inverse relation. So if we started with y equals x cubed plus x equals y cubed plus y would be the inverse relation. Now, if that new relation also satisfies the condition for a function, then instead of calling it an inverse relation, we call it an inverse function. Okay. Now, the common symbol we use for inverse function is to put a -1 next to the f. Now, that does not mean the reciprocal. So it's not saying it's to the power of -1. It's just saying it's the inverse function. If we were to look at both on one number plane, then the function and the inverse function would be reflected in the line y equals x. Do you remember we said we obtain them by swapping the x and the y value? So obviously on the line y equals x, those are the same anyway. And so that becomes the reflection point for this new inverse function. So if AB is on the original graph, then BA would be on the new inverse. And the domain of the original would become the range of the inverse. And the range of the original becomes the domain of the inverse. So basically all the x's and the y's are swapping round. So how do we test? Again, the easy way is visually. Because if we're swapping the x and y's around, and we know the test for a function is a vertical line test. So if I want to look at the original curve and work out whether it has an inverse, then I can use a horizontal line test. Because now I'm swapping the x and y's around. So instead of being vertical, I go horizontal. So if we look over there at our graphs on the wall there, the parabola, would it have an inverse function or an inverse relation? Yeah, just a relation, because it's going to fail the horizontal line test. What about the hyperbola? Function, that one's okay. It'll only ever cut it once. Cubic. What about the circle? No, gotcha again. Because the first condition is y equals fx has to be a function, and the circle's not a function. So it can't have an inverse because it's not a function in the first place. Here's our parabola. Horizontal line test. Oh no, cuts it twice. So no, it will only have an inverse relation. Whereas the cubic, there's my dodgy cubic. Doesn't matter where I put the horizontal line in. So it has an inverse. So that's great if we know what the picture looks like. Okay, the other way. If you don't know what the picture looks like, or we had to prove it a bit more formally using algebra, so what we do is we rewrite it, we swap the x and y's around, but then try and make y the subject of the new one. And if it's unique, then it's an inverse function. And if it's not unique, it's not. So what do I mean by that? Let's have a look at our parabola. So swap the x and the y's around, it becomes x equals y squared. And I want to make y the subject. I'd go, oh, well, y equals plus or minus the square root of x. So it's not unique. You get a plus and a minus. So no good. It's not unique. Whereas the cubic, if I swap the x and the y's around, x equals y cubed, the next becomes the cube root of x. Now, when we're dealing with real numbers, there is only one cube root. Obviously, with complex numbers, we know there's 3 of them, but in the real world, there's only one cube root. So that is unique. So yes, it does have an inverse function. So that's how we can prove it using algebra. All right, this is a bit of a mouthful. If the inverse relation of y equals function x is a function, so in other words, we just swapped the x and the y's and we found that it was unique, or it satisfies the horizontal line test, then y equals function x has an inverse function. So that's what we're saying. We've just determined that this new thing that we've created is an inverse function. Then what should happen is that if I substitute the function into the inverse function, I get x. Because inverses cancel each other out. That's the basis of solving equations. If I want to undo a mathematical operation, I do its inverse. And if that mathematical operation happens to be a function, like y equals log x, then to undo the log, I use the inverse. And the inverse of logs are exponentials. That's the inverse function of a log function. So that's all that's really saying. But the reverse should be true as well. If I substitute the inverse into the function, I should also just get x. So here's one. It's a hyperbola, if you don't recognize it straight away. It's been shifted a little bit. So it should have a function. Let's work out the inverse. I'll swap the x and the y's round, and I get x equals 2y plus y on 3 minus 2y. I'll make y the subject, and sure enough, it's unique. 3x minus 1 on 2x plus 2. So all right, let's substitute the original function into the inverse. So everywhere there's an x, I'm replacing it with 2x plus 1 on 3 minus 2x. Yuck. Fraction on fraction. So all right, multiply everything by 3 minus 2x. We'll tidy that up a little bit. And then we can play around with the algebra. And sure enough, we do. We end up with x. But the reverse should be true as well. So let's do that one as well. So this time, in the original function, everywhere I see an x, I've substituted in the inverse 3x minus 1 on 2x plus 2. And again, playing with the algebra, multiply everything by 2x plus 2. Again, we come down to the x. Of course, most functions will not have an inverse. Because as soon as you have a turning point, it's going to fail the horizontal line test. And if you think about all of the different types of functions that we looked at, certainly polynomials, sine curves, cosine curves, tan curves, they all would fail the horizontal line test. So in order to create an inverse, we restrict the domain of the original function and say, look, I only want to look at a piece of the original function, and this will create an inverse function that I can use. So any function that we don't have an inverse, we can create an inverse by restricting that domain. Now, when I try and restrict it, I want to capture as much of the range as possible. So y equals x cubed. The y equals x cubed is going to be okay, because remember, it had an inverse. So let's have a look at it again. There's my dodgy y equals x cubed. The domain is all real x. The range is all real y. You know, in hindsight, this is possibly not the best example to pick. Because look what happens. When we swap the x and the y around, we get y equals x to the power of a third, and the domain and range swap around. Now, you might be looking at that and thinking, no, they're just the same. No, they're not the same. The domain is the old range. So that all real x came from that all real y, and the range, that all real y, came from the domain all real x. So the domain and the range have actually swapped. As I say, in hindsight, possibly a bad example to use. If we were to draw it, I've just drawn in a faint y equals x there. We would reflect it in that line. So any point on y equals x will stay the same. The other point, I would draw any turning points, x-intercepts, y-intercepts, and reflect that at 90 degrees through y equals x. And we get, there it is, y equals x to the power of a third. And if you tilt your head at 45 degrees, you'll go, oh, look at that. It is symmetric. All right, let's try a function that we know already what its inverse is to show this a little bit better, I suppose. So there's our exponential y equals e to the x. And remember, that's our one that goes, whoop, asymptotic on the negative side, cuts at 1. Its domain is all real x. Its range is y is greater than 0. So create the inverse. X equals e to the power of y. And as I said, we've already seen that the inverse function is the natural log function. So y would be log x. The domain is x is greater than y. So this is a better illustration of the range of the domain swapping around. So the range of the original curve was y is greater than 0. The domain of the new one, x is greater than 0. And the range of the new one, all real y, because the domain of the original was all real x. And if we were to draw that one, and there's our log curve. Notice the log curve and the exponential curve never intersect. They have no point in common. Let's have a look at y equals x squared. Here's one where we said, hey, it doesn't have an inverse. So there's y equals x squared. Oh, sure enough, it's going to fail my horizontal line test. Domain's all real x. The range is y is greater than or equal to 0. So no good, no inverse. So we just want a piece of this parabola to capture as much of the range as possible. Now obviously there's different pieces I could take. There's two obvious ones, I guess. One where I'd take all the positive x values, one where I take all the negative ones. What we try to do is, if we can, include the origin, which we can in this one, and tend to go with the positives rather than the negatives. So I'm going to restrict my domain to be x is greater than or equal to 0. So if we look just at x is greater than or equal to 0, then it would satisfy that horizontal line test. So the range stays the same. I've captured all of it. So my new function, y equals x to the power of a half, its domain, x is greater than 0, or greater than or equal to, y is greater than or equal to 0. Reflect that in y equals x. I could have picked the other one. I could have restricted my domain to be x is less than or equal to 0. But then my inverse function would have become y equals negative x to the power of a half, and I would have got the lower half of the parabola. Let's have a look at HSC1. This function is e to the power of minus x squared. Okay. It has 2 points of inflection. Find the x coordinates of these points. All right, so a bit of calculus to start off with. Possible inflection points we know. Second derivative equals 0. So let's find the second derivative involved a bit of work. But there's our two possibilities. Plus or minus 1 on root 2. It just said find the x coordinates. Now, do I need to test these points? Opinion. Now remember, I've always said, whenever you're finding points of inflection, these are possible points of inflection. To confirm they are points of inflection, you would go and test them. So would you go and test this? In this case, no. They told me it has 2 points. I've found 2 possibilities. Well, if there are only 2 possibilities, and they've told me there are 2 points, these must be them. So in this case, I don't actually need to go and test it. All right. Explain why the domain of the function must be restricted if it's going to have an inverse function. What did I say? Oh, I went very technical. Look at this one. Woohoo. In order to have an inverse function, there must exist a one-to-one relationship between the domain and range. In other words, every value in the domain gives a unique value in the range. That's a pretty cool definition. You could probably say it failed the horizontal line test. Or you could say, I guess for a particular y value there exists 2 x values or something like that. All right, we're going to find a formula for the inverse. They've told us what the restriction is going to be. It's going to be x is greater than or equal to 0. Swap the x and the y's around. So x is equal to e to the minus y squared. Minus y squared is log x. Y squared's minus log x. I brought the negative in as a power because I'm always uncomfortable with y squared equals negative. So I've made a log of 1 on x, and then y would equal plus or minus. But we have restricted our domain to be x is greater than or equal to 0, which means the range of the new function will be y is greater than or equal to 0. Therefore, which one do I take? Positive or negative square root? Right, because the range has to be y is greater than or equal to 0. So y is greater than or equal to 0. So our particular inverse function will be the square root of log of 1 on x. State the domain of the inverse. Well, the domain of the inverse will be the range of the original function when we did the restriction. And so, looking at the original graph's range was between 0 and 1. 0 wasn't included because it was an asymptote, but 1 was. That will become the domain of the new one. So x is in between 0 and 1 with 1 included. Sketch the curve. It's a reflection in y equals x. There we go. Fortunately, I could scan mine and go like that. So basically, it's now going the other way, up the y-axis, but it's just the positive part. Just the positive part. All right. Time to play.